Have you ever wondered how we manage our precious underground water resources, predict the spread of contamination, or design effective groundwater remediation strategies? All these vital tasks relying on our ability to understand and foresee the complex journey of water beneath the Earth's surface. But how do we truly map out the invisible flow of this essential resource and make accurate predictions for its future? Hydrogeology plays a foundational and indispensable role in hydrological modeling by providing the scientific understanding of groundwater systems necessary to build accurate and predictive models. It furnishes the essential data and conceptual frameworks that transform theoretical equations into practical, real-world simulations of water movement and contaminant transport. The core reason hydrogeology is so critical lies in its focus on the physical and chemical properties of aquifers, which are the underground layers of rock or sediment that hold and transmit groundwater. Hydrogeologists determine key parameters such as hydraulic conductivity, which measures how easily water flows through a material, and storativity, which indicates how much water an aquifer can store or releases. They also identify the extent of an aquifer, its boundaries with less permeable layers, and the locations where water enters or leaves the system. Without this detailed geological and hydraulic characterization, any groundwater model would be built on pure speculation, rendering its predictions unreliable and potentially dangerous for water resource management or environmental protection. Practically, hydrogeology informs every stage of groundwater modeling, from initial conceptualization to calibration and validation. A hydrogeologist first develops a conceptual model of the site, outlining the geological formations, water table configurations, and potential contamination sources. This understanding then guides the selection of the appropriate numerical model, whether it is a finite difference model like ModFlow or a finite element model. Hydrogeological data, including pump test results, water level measurements from monitoring wells, and geological logs, are then used to populate the model with realistic parameters and boundary conditions, ensuring the model accurately represents the subsurface environment. One insider detail that underscores hydrogeology's importance is its contribution to understanding the full groundwater budget, accounting for all inflows, outflows, and changes in storage. Hydrogeologists use isotope hydrology and geochemical tracers, for instance, to determine the age of groundwater and its recharge pathways, adding a crucial temporal dimension to models that simple flow equations cannot capture alone. This deep understanding allows for the simulation of complex processes such as groundwater surface water interaction and density-driven flow, which are vital for coastal aquifers and saline intrusion studies. It ensures that models are not just mathematical constructs, but robust representations of dynamic natural systems. Ultimately, the rigorous application of hydrogeological principles to modeling empowers us to make informed decisions about water allocation, groundwater withdrawal rates, and contaminant migration forecasts. By integrating geological insights with hydrological processes, we gain the foresight needed to sustainably manage one of our most vital natural resources, ensuring its availability and quality for future generations while effectively mitigating environmental risks.
If you love learning about water, like, subscribe, and keep exploring with us.